Welcome to Dreamforce, everybody. We're pretty early in the week, so hopefully everybody's high energy. I know I am, excited to be here. My name is Scott Persinger. I'm here with Pavel Pravasud today. We are from Heroku. We want to talk a little bit about how we're using the new Apache Kafka and Heroku service internally within Heroku. Before I get started, I want to just get a quick sense of like who's out in the audience, what you know. So if we can get a show of hands first on who has heard of Heroku at all. Oh, awesome, okay. Who thinks they know what Heroku does? Okay, pretty good. And who has actually deployed or is running an app on Heroku today? Awesome, fantastic, okay. Well, that's good. That's gonna make my job easier today. All right, forward-looking statements, our safe harbor, blah, 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 blah. You'll hear this many times this week, and many other speakers will give you a better summary of what's on this slide. If you want a copy of this, come up to me after the show, and we'll get you sorted out. All right, a little bit of Heroku 101, just for anybody who's not 100% familiar with our platform. Heroku is a platform for building, deploying, and scaling web applications. Now, these applications can use a variety of languages, including Ruby, Java, Go, Python, PHP, Node.js. They can use any kind of open source framework. And so Heroku is a great platform for building and deploying customer-facing custom applications. So a lot of what our customers are doing with Heroku today is building custom mobile applications or web portals for their customers, and using a lot of great open source technologies to help enable that. Another great service that Heroku offers is a synchronization service called Heroku Connect. And this service will allow you to pull data directly in from your Salesforce org, make it available to your custom application, and also sync data back. So if you build like a customer portal, that application can directly use information from Salesforce and can push information back. So if you're interested in learning more about Heroku Connect or Heroku in general, I encourage you to visit the Heroku pod in the Trailhead, which is downstairs. Or you can ask Pavel and I about it after the presentation today. So beyond our platform for running and scheduling applications across our container platform, Heroku also offers a suite of data services. Our most popular is Heroku Postgres. This is the master database underneath hundreds of thousands of applications that are deployed on the platform today. A fully managed service, managed backups, performance monitoring, error monitoring. Heroku Postgres is an awesome service. If you haven't used it before, I encourage you to check it out. We also offer Heroku Redis for caching and queuing use cases. But most recently, we launched into general availability Apache Kafka on Heroku, and that's what we're going to talk about today. Now, Pavel and my team at Heroku, we had some early access to the Apache Kafka service, so we've been using it since January, and what we're going to do today is talk about some of our experience using the service. So Pavel and I come from a team at Heroku called the Core Services team. So we're not actually on the data team. We run application, which is really the central orchestration application for the Heroku platform. So Heroku provides a command line interface and a slick web dashboard for interacting with Heroku. You can create applications, you can provision new databases, you can scale your application up on multiple containers or scale it down. All of those interactions work through the Heroku Platform API, and that's the API that we manage with this Core Services application. So identity, authorization, anything to do with apps and add-ons. But Core Services is really just a front end to the Heroku platform. And in fact, the platform itself is composed of over 100 different services and components that run in production and have to integrate together. So a lot of what we're going to talk about today is how our core services application, this central orchestration application, is integrating with these other components that form part of the platform. So you can see a build system, app execution, billing. That's just like the tip of the iceberg in terms of all the other services that are running. So here's the big idea. A couple years ago, we started this move from synchronous system integration to more of an asynchronous event-driven pattern. So traditionally at Heroku, we've integrated systems together with what I think of as kind of a traditional RPC mechanism. We make synchronous HTTP calls from our system core services out to like the build system. Or, generally speaking, system A talks to system B. We also have some patterns where we have systems like for building a data warehouse that just reach directly into our database and pull data out. I consider this kind of like traditional RPC style integration. So a couple years ago, we started down this path of revamping a lot of that around more of an asynchronous event-driven pattern. And then this year, we deployed Kafka as the messaging broker to power that integration. So that's really what we're going to talk about today, is how we're using Kafka to power asynchronous event-driven integration pattern within the Heroku platform. So what we did was we created this abstraction that we call the platform event stream. And this really represents a logical stream of changes and state changes that are coming off of the Heroku platform. So the core services application exposes a RESTful API out to the world. This is documented in our platform API reference. We define a set of resources, and you can perform essentially CRUD operations against those resources. So the core services application handles those API calls, mutates state around kind of typical application models, saves that new state into the database. But now we also, along with that save call to the database, we generate a logical event that represents the change in state, and we publish that event onto our Kafka cluster. And now downstream systems can listen to those changes. What's interesting, or one interesting way to think about this platform event stream, it's very analogous to database replication. If you've worked with MySQL database replication or Postgres database replication, both these systems have this notion that the master server generates a stream of change events that downstream servers listen to, they replay those changes, and in effect replicate the state from the master. So our platform event stream is a similar idea, and the key difference is that it's a logical event stream. It's representing logical events, and thus it's independent of our database schema. If we make any changes to the database, or even any sort of internal application changes within the core services system, we can still be generating the same set of logical events, and this is the thing that our downstream systems are listening to. So what are the advantages of this kind of approach? The biggest thing that we were wrestling with at Heroku was we have many engineering teams, let's call it 20 separate engineering teams at Heroku, all working on different components, different parts of our service. And over time, what we realized was that these synchronous integration points from service A to service B were really hard to manage. It meant that any time service B changed or needed different data, we would have to change both sides. We have to make a change in core services and in the downstream system. And over time, as these point-to-point integrations become more numerous, they become harder to manage and harder to sort of reason about, and harder to manage the growth and evolution of those systems independently. So the big advantage we're getting out of this asynchronous event-driven system is the platform event stream is now this logical contract between us and downstream systems. There's also a physical intermediary, the Kafka cluster itself. So a downstream system can be down, it can be restarted, it can be under maintenance. It's no problem. Kafka is going to queue up changes, and that downstream system can come along and replay those changes whenever it's interested in hearing about them. So what this is really enabling is for us to have multiple teams working on systems independently, and those systems changing and evolving independently over time with this level of indirection safely between them. Now, these advantages don't come without some cost, right? And so you can see I've listed some of the disadvantages up on the screen here. Probably the biggest one is some of these asynchronous message calls actually implement a workflow that crosses across multiple systems. So the problem now is it's harder to track the status of those requests, right? A user initiates an action, I publish an event to Kafka, and some downstream system receives that event, and it triggers its own workflow. Well, if there's an error, you need some channel now to communicate that error back to the user. You're not within the request response flow where it's easy to just send the error message back to the user and, oh, you need to retry this or enter different input parameters. So generally, trying to trace requests and track down things like performance problems across our system has become harder as we move more to an asynchronous model. Just check my notes here quickly. So I'd like to turn it over now to Pavel Pravasud, the lead engineer on the core services team, and he's going to dive into some of the details of how we're using Kafka.
Hi. So my name is Pavel. I'm going to talk you through some implementation details of the platform event stream. It's important to understand that the platform event stream that we have right now didn't come out of nowhere. It is, in fact, current implementation is the third one we've employed. It all started a couple of years ago when we needed some sort of audit log for support purposes and some other stuff. So we just started by, saving a bunch of random free-formed events into our database table. And it all kind of worked fine for a little bit, but then obviously we ran out of database, and the volume of the data was so big that we have to extract it into its own database and provide some sort of service around this and some sort of query interface. And at this point, we start realizing that having this data around and being able to query it and stream it has a lot of benefits. And again, database wasn't really the most convenient backend for this kind of system. So we kind of introduced a next generation of the stream, which was based on Amazon Kinesis this time. And a lot more effort was put into designing the event schema this time. And we decided to go with the very strict format. The example you can see here on the slide is you see each event has a unique ID, which we use UIDs because it's convenient. We explicitly mention the event type and event action. The resource type and event action. In this case, it's an app, and we're creating an app. Every event originates around a certain actor. A user initiates this event, so we save this actor information here. Then we have a data field, which is basically a serialized version of the app in this case. It can be any kind of record in the system. We have this optional field called previous data. It only makes sense for change events, obviously. If this is a change event, previous data contains the fields and their values prior to the change. So the consumer can evaluate every single change, like what it was and what it is now. There's obviously some kind of a little bit more free-formed and less structured metadata. And then all events have a version designation and a create data field, which is just a UTC timestamp. So this all worked fine for us, and at some point we start running into problems with Amazon Kinesis. So we pretty much just took this version of the stream and migrated it from Amazon Kinesis to Kafka. And why did we have to do this? Let me tell you a little bit about Kafka. So Kafka is an open source project currently developed by Apache Software Foundation. It was initially created on LinkedIn with the aim to provide a unified high throughput, low latency platform to handling real-time data feeds. That's their official statement. It is basically a massively scalable pub/sub message queue architecture for distributed transaction log. It makes it highly valuable for enterprise infrastructures process streaming data. This design is heavily influenced by transaction logs. The main idea behind Kafka is that it's somewhat similar to other well-known products like RabbitMQ or IBM MQ, but its implementation is quite different and unique. It puts a lot more responsibility on the client and external synchronization and coordination. So it makes the core design of the system a lot simpler, and it leads to way better overall performance. So LinkedIn was recently purchased by Microsoft, as you all know, and in one of the recent presentations, Microsoft claimed that they are pushing around 1 trillion events through their Kafka cluster a day. That kind of gives you an idea about what kind of performance Kafka is capable of. So let's look at some high-level architecture overview here. A typical Kafka cluster consists of several brokers, and they're coordinated by an instance of Zookeeper. The data from producers gets replicated across multiple brokers using this thing called partition. We're going to talk about this in a second. The replication are controlled by a setting called a replication factor. So because of its distributed and redundant design, this architecture is capable of surviving a loss of almost half of the brokers in the cluster without any capacity or data loss. So also allows cluster to automatically recover and like restore lost brokers without kind of completely transparently for both producers and consumers. Okay. Let's talk about the some core Kafka primitives. One of the most important one is called a topic. Topic is essentially a message channel. It represents a logical stream of related events. Producers send messages that are appended to the head of the log, and then consumers read from the tail of the log forward in time. If producers are consumers read from the tail of the log forward in time. If consumers are fast enough, they eventually catch up with the producers and start reading directly from the head as producers append messages to the head. It kind of gives you a real-time streaming. A single topic is broken into multiple partitions. Partition is another core primitive that enables replication and parallel processing. Producers have control over which partition each event goes to. You can enable this control, sort of, or you can just basically get some random assigned partition for each of your events. It is important to understand that because partitions are typically consumed in parallel, there is no ordering guarantee within a topic. You can get an ordering guarantee only within a single partition. Each event in the partition has a unique auto-incremented number called offset. This data is available to the consumers, so each consumer knows what offset is currently consuming. You can kind of use this data to remember where in the stream you are. So if your consumer crashes or needs to restart or something bad happens, you lose your network, every time you reconnect, you can start consuming from a specific place in the stream and not just some random position. In some cases, you might even want to replay some of the events by just going back to an older offset and reconsuming the events that you already consumed previously. So let's talk about producers a little bit. So here we have a very severely simplified Ruby-like code that is used to produce an event. In this case, this is an app create event. Obviously, real code doesn't look like that, but it kind of gives you the idea. So as you see, we specify the event action here. We provide actor information. We just plug in the serialized version of the app that we've just created. And one of the really important things to take notice here is this field on line 16 called partition key. Partition key is very important. And in this case, we're using API UID as a partition key. Partition key controls which partition in the topic your event goes to. So because we want all events around the same app to go to the same partition at all times, so we can get like ordering guarantees within the app, and this kind of prevents a situation where you get like an app update or app delete event before app create. Okay, now the consumer part is a little bit more complex. First off, there's more than one way to consume Kafka topic. One of the most kind of preferred and more advanced way involves this concept called consumer groups. You have a little diagram here on the right side of the slide. Basically, consumer groups are these kind of dynamic structures that make let you dynamically assign, like add or create or remove consumers. The way it works is there is some coordination happening between the client and the cluster involving Zookeeper, and it kind of enables, it automatically distributes the load between your consumers. It also can detect like when consumer goes away for whatever reason and rebalance the load. So when your consumer is down, like none of the data is lost and others kind of take its part, you know. This kind of setup really gives you the ability to build extremely performant systems because you can have almost as many consumers as you want. Consumers consuming data. There is also, of course, a more primitive approach that involves connecting to each partition directly, providing an offset you want to start consuming and just reading. And this is kind of the approach that we took with our platform stream. And one of the reasons we decided to go with that approach is, well, first off, the third-party library support wasn't very great for consumer groups at the time when we started. And then we also wanted to be as similar as possible to our existing Kinesis implementation that kind of worked on a more primitive level. It didn't have this concept of consumer groups at the time. So let me show you a little demo about the way we consume the stream. So this is not my machine, so it's going to be a little awkward. Okay. So I wrote oops. I don't see my own screen, so it's really, really hard to type. Okay, I wrote a little script that connects to event bus and just kind of reads events from there. We start from at the current head, so we're not replaying any events right now. As you can see, like we just have a little counter here running. Nothing really is happening. What this little demo is doing, it is listens to the events of the one specific apps, and it listens for one specific type of event, which is a resize. So I'm just going to go and resize this app. This is the app. It's called DF16 Event Bus Replay Demo. Where's my mouse? I don't see my mouse. How am I supposed to resize things? Okay, there we go. The app doesn't really do anything useful. There we go. As you see, there's an event of Scott resizing the app. This is the new state. This is the previous state. We can resize one more time. Okay, so this is kind of a real-time consuming. Everything works great, but then let's assume that our consumer crashed. Something bad happened. Maybe it lost network. Maybe there's a bug in software, whatever. So we're not consuming right now, but your customers don't really stop resizing their apps while your consumer's down. So let's just make a few changes here. 1, 2, and just one more for good measure. So our consumer is down, but we have a thing called offset saved somewhere. In this case, it's just really primitive. It's this in this little file. As you can see, there's like, for each partition, there's this huge number. So we can just kind of start resume the consuming from this place where we stopped last time. And let's try that. And if the internet gods are merciful. There we go. And we see 1, 2. OK, all the 3 events that we missed while the consumer was down. So this is kind of the idea about, around replayability. Kafka provides, at least in our settings, it provides us 7 days of retention. So our consumer could be down for 7 days and then completely recover itself. Let me go back to this. OK. So since we introduced the platform event stream, and we introduced the latest version in January 2016, we saw a really, really rapid adoption and growth of usage. And on this slide, you see like a bunch of services that were built around this platform event stream. And this is not even all of them. One of my favorite ones is the detection response, which is built by our security team. It listens to the stream and it tries to detect platform views when people are doing crazy things like mining bitcoins or just trying to build botnets on top of free accounts. The best part about this slide is that I have no idea how most of these services work or what they even do. They were built by different teams completely independently. There was no integration code in kind of our code base. There was no kind of coordination or anything. They could just kind of start consuming the stream and build their own thing and kind of not really spend much time on like trying to integrate with us. So this kind of shows you how it boosts productivity, I guess. We were also very happy with the performance. The slide says we have 20 consumers. This is not actually true. The real number of consumers is somewhere between 30 and 40 right now, I think. So I've built a little performance dashboard on top of Librado that monitors the Kafka event stream like in real time, and it measures the latency between the time event was created on the producer side and it is fully recovered and consumed on the consumer side. And the typical latency of the whole stream is 250 milliseconds, which is pretty good. You could say it's real time. Where's my mouse? Anyway, here on the right side of the slide, you can also see the screenshot of Heroku Kafka dashboard. Again, the numbers here are very off. The real numbers are way higher than this. I also want to mention that we are running the 8-node cluster right now, 8-broker cluster. We don't really need that much. It's just nice to have this incredible capacity and not think about this ever. We can introduce new streams or new event types without ever thinking about capacity. Sorry about that. OK, we're also using Kafka 0.10 at the moment, which is the latest version. We started at 0.8 back in January, and then since then we were able to like completely seamlessly and transparently upgrade to 0.9 and then 0.10, and none of our consumers notice anything, which is great. And I think this is pretty much all I have. Let me turn it back over to Scott. He has another cool demo for you.
Great. Thanks, Pavel. So what I wanted to do, what Pavel showed was kind of like the the simplest possible demo, almost like the hello world for the platform event stream. We also have a quick demo I'm going to show here. There we go. So this is a little bit more looking at stream processing. So our use case currently within Heroku is primarily focused on system integration, application integration. But what's really interesting is to start thinking about looking at this stream of data in more aggregate ways. So this little application I built is like the simplest possible version of this aggregate view of the stream. What you're seeing is like the raw events just getting thrown up on the screen at the bottom there. And then on the top, we're just counting the number of events. So we have like new apps that we've seen. We're seeing application deploys, containers getting started, what we're calling one-offs. And then the dark blue is the scale events. These are the events that Pavel was showing earlier. So all that this application is doing is just counting these events, and then it's generating a little data point every 2 seconds, and we're putting it up on this graph. So you get a sense for how much data is coming over in this stream. And I wanted to show this as just a quick demonstration, a quick sort of pointer ahead at looking at stream processing over this data. And this is where sort of Kafka's power really, gets exciting, opens up a whole set of opportunities that for doing kinds of analysis that are really prohibitive to do with just a relational data store. Like this is sort of traditionally what you would do is like build this huge data warehouse, and you try to process it with SQL queries that could take a long time, be really painful to try to get this kind of aggregate view of the activity over your entire system. Oops, alrighty. There we go. All right. So what are our lessons learned? We've been really happy with the asynchronous integration pattern powered by Kafka. Really happy in terms of innovation internally, the ability for new groups and new teams to start consuming our stream and building new applications and services. We have some additional teams that have started publishing their own streams of data and using it for their own purposes on top of their own Kafka cluster. So we're seeing this pattern get repeated even beyond just the core services platform event stream. We've been really happy with reliability and performance of the Kafka cluster. We've done 2-point version upgrades now that we were able to do without any downtime of the cluster itself, any impact perceived by clients connected to it. And the best part for us is having the Heroku data team running this cluster for us. Actually running and administering Kafka is a non-trivial sort of exercise. You're talking about a multi-node cluster with Zookeeper involved, data storage management, and all of these things are handled completely transparently by Heroku data. And any Heroku customer now can get that same thing by signing up for the Heroku Kafka service, which is pretty cool. It does require a shift in thinking from the development side to shift from kind of a traditional querying data out of my database kind of pattern to thinking about reacting to events. It's funny because I actually think the Node.js and the front end guys are more in this mode already. Things like React and Redux are really pushing this notion of building applications in this pattern of reacting to events as they come in. And this is really applying that same kind of notion to our back-end systems, triggering workflows based on actions that are occurring rather than always driving everything through the web request coming in. So there's a bunch more talks and sessions at Dreamforce this week that are going to be delving into different aspects of Kafka. There's a session later today from some people at Yelp talking about real-time data integrations with Kafka. There's going to be a really interesting session tomorrow, which is from a colleague here at Heroku talking about scaling on Apache Kafka and really talking about the big data use case for Kafka, it's going to be a super cool talks. So I encourage you to check those out. You can also just search for Kafka on the Dreamforce agenda. There's a bunch more talks than the ones that I've shown up here. Or come by the Heroku booth in the developer forest, and we're happy to give you a demo or talk more about it. So that's all we have today. Thank you very much for coming. Really appreciate everybody's attendance. Pavel and I are going to stick around for questions, but people probably have other sessions they got to get up to as well. So I appreciate everybody coming today. So if you have questions, I think there's microphones floating around the audience. Maybe stick up your hand. Somebody will come find you with a microphone. The lights. We don't need the lights. Yeah.
Moving the Heroku Connect to leverage the Kafka architecture?
That's a very good question. So we are not directly
Can you
involved.
repeat the
question? So the question was, do we have any plans to change Heroku Connect to leverage Kafka? That's a very interesting and very complicated question. And we're not that close to the Heroku Connect team right now. What I would say is come by the Heroku booth, and there'll be some people there demoing Heroku Connect, and they may be able to talk more about its possible event-driven future. Yep. Yeah.
It looked like you guys were using this primarily for like event listening and audit logs. Are you guys using it at all for any kind of task processing?
Any task processing?
Right, like queuing up jobs for workers to go execute?
Yeah. Well, that's not true. So we are in the sense that we definitely have systems that are listening for events and triggering their own workflows. We still have some older kind of batch style, job queues in the database kind of task processor systems. So we're kind of gradually migrating over to that model.
I kind of can add to this a little bit. So Kafka itself is not very good at as a primary backend for your job processing systems because of its distributed nature. It cannot give you exactly once guarantees. So everything you put into Kafka can potentially come out more than once. And this is not great for any kind of job processing backend. Like if you want a delayed email being sent, you don't want this email to go out twice. So you can use Kafka as intermediary delivery mechanism to your some sort of job processing service, but you don't want to queue jobs itself in Kafka.
So is something like RabbitMQ more suitable for a role like that?
Probably. You basically want some sort of strong guarantees that everything, right. You're either not losing data at all, and everything that is being put into your system once comes out exactly once, and Kafka does not give you that.
Well, or you have to implement that idempotency for your jobs on the consumer side.
Yeah, correct.
Keep track of work that's.
So in one of the slides, I had this event schema, and it had a UUID. We actually use those UUIDs to kind of enforce idempotency, because every UUID that we've seen once, we do not process again if we see it.
So our usage currently is purely internal. We're looking at how to both expose, so we're exposing the service to other applications purely through the Heroku data service, right? You can come and configure provision your own cluster and start using it for your own applications. We're also looking at exposing our platform event stream as a user consumable stream. It isn't there, we haven't worked out all the bits in terms of authorization so that you get access exactly to the events that that you should get access to. So that's kind of a future direction that we're looking at.
Will you be ever opening it for Heroku applications, user applications to be publisher of the events?
Yeah, so you can use it today. You can provision a Heroku, a Kafka. You get your own cluster today, and you can use it within your own application. Yeah. We're out of time. Okay, so we're out of time. Pavel and I will be hanging around outside, but I think we got to free up the room. But yeah, come find us outside if you got more questions.